Welcome back everyone. In this lecture I will actually prove some of the properties of the roots, so which will be used later in the classification of semi-simple algebras. So, let us begin. So, first I will recall what we have done so far. So, we started with G being finite dimensional semi-simple algebra. Over C, and then we have chosen a maximal toral subalgebra. So, let us say H is a maximal toral subalgebra of G. So, that means, so the elements of H, they are all add semi-simple elements. Okay. So, elements of H are all add semi-simple. So, that means elements inside G. So, that means add x. So, when you take x from H, they all act semi-simply on G, act semi-simply on G. So, now not only that, any toral subalgebra we proved that it must be abelian. So, in particularly this H is actually abelian subalgebra of G. So, in particularly, so if you take this adjoint action and then restrict it to H, so then each element of H act semi-simply on G. Since they all mutually commute, so all the elements of H acts simultaneously diagnostically on G. So, in particularly we can talk about root space decomposition of G. So, let us recall what it is. So, you write G as G naught direct sum G alpha, where alpha coming from phi. So, where G alpha is defined to be, so those x in G such that when you act by elements of H via adjoint action, then that actually gives us alpha of H x for all H in H. So, this is the definition of G alpha for alpha in H star. So, in particularly G naught is defined to be the centralizer of this H. So, which is those elements of X that commutes with H. So, we indeed proved that this G naught is nothing but H itself. So, if we start with maximal toral subalgebra, then the centralizer of that maximal toral subalgebra inside G must be equal to H. So, this is something we have already proved. So, with this we have this root space decomposition. So, let me write it again. So, G is equal to H direct sum G alpha in phi. So, that is how we have. So, where phi is nothing but those alpha in H star difference 0 such that this G alpha is being non-zero. So, these elements of phi, they are called roots. So, these are all the set of roots. Of course, these roots are associated with G with respect to the action of H. So, then we can say that this is the set of roots. So, with respect to the pair G comma H. Okay. So, now these G alphas we already seen that for alpha in phi we call this G alpha as root spaces. Okay. So, in particularly we have what is called this root space decomposition of G. With respect to, of course, the Cartan that we have fixed. So, what we want to do now, we want to understand the properties of these roots as well as the properties of these root spaces. So, indeed we will prove that all these root spaces, they have dimension 1, and this set of roots they will form a root system in the sense of, so we will define what it is later. Okay. So, before moving forward, we will actually recall some of the facts that we have already proved. So, we have this killing form that is defined on G. So, when we restrict this killing form to H, that must be non-degenerate. So, killing form that is defined on G, that is non-degenerate, and again if you restrict that to this maximal toral subalgebra, so that is also non-degenerate. So, this is something we have already proved. So, we also proved something more about these orthogonality relations between these root spaces with respect to the killing form. So, if we take kappa of G alpha and G beta, so that will be always 0 if alpha plus beta is actually non-zero. So, you take alpha beta inside H star such that this alpha plus beta is non-zero. So, then this G alpha and G beta, they must be orthogonal to each other. So, these things we have already proved. So, let us use them and then derive some properties of this set of roots. So, what we do now, we just want to prove various properties of these roots. So, let us fix this notation phi, which is as above. So, let us say phi, this is the set of roots. So, with respect to that pair G comma H. So, this is something we are fixing. So, now what is the first fact about this phi? So, this phi, if you take as a subset of this H star. So, first of all this is a finite subset. So, this is a finite subset of H star, and note that 0 is not in phi. So, this is one important property. So, if we think about it, actually if we take this span of this phi, so then that must be exactly equal to H star. So, this is something one can prove. So, on the contrary, assume that this span of phi is actually proper. Okay. So, otherwise let us say this span of phi is proper. So, this is our claim, span of phi must be equal to H star. So, now if we look at the dual space of this, so that means the dual of this fan phi inside H. So, then what we get? So, then there exists H inside your H which is non-zero, such that this alpha of H will be 0 for all H in H. So, this is one can get it from by looking at the dual of span phi inside H. So, because there is some H in H such that which is non-zero element such that alpha of H is 0. So, then we can simply calculate how this H will act on G. So, recall that. So, H is going to act on H by 0 for all H dash in H, and if you compute H with any x, where let us say x is coming from G alpha, then this bracket H x is nothing but given by alpha of H x. But since alpha of H is 0, so you get the bracket H x is equal to 0. So, this means this bracket of H G alpha is 0 for all alpha in phi. So, now put together all this, you can see that the bracket H with G is actually 0. So, that means H must lies inside the center of G, but we know that since G is semisimple Lie algebra, the center must be 0. So, that proves that H must be 0, which is actually a contradiction, because we started with H which is non-zero. So, that means this span of phi cannot be actually proper. So, it must be equal to H star. So, this is something very important property of this set of roots. So, now let us see other properties. So, the second property, if we take alpha from phi, so then one can prove that minus alpha also must be inside phi. So, indeed we will prove that if alpha is in phi, then plus or minus alpha are the only multiples of real multiples of alpha inside phi, or even complex multiple of alpha in phi. So, we will do that later, we need some SL2 representation theory to prove that, but this fact is easy. Let us say you have alpha in phi. So, if this is not true, let us say it is not true. So, then there exists alpha in phi such that minus alpha is not in phi. But then look at what happens to the killing form. Okay. If I take the killing form with G alpha with G beta, so then this must be 0 for all beta in phi, not only in beta and phi as well as for beta 0 also this must be true. Why this is the case? Because alpha plus beta will be never 0, because beta cannot be minus alpha or beta, yeah, if it beta 0 again it cannot be minus alpha. So, that says that alpha plus beta being never 0. So, that implies the kappa of G alpha comma G beta must be 0. But then this implies immediately that kappa of G alpha with G that must be 0. So, that means G alpha lies inside the radical of kappa, but since kappa is non-degenerate, so the radical of kappa must be 0. So, that implies that G alpha must be 0, but that is contradiction for the definition of elements of phi, because we collected elements of phi so that G alphas are non-zero. Okay. So, this is a contradiction. So, that proves that the bracket sorry, if alpha is in phi, then minus alpha also must be in phi. So, now we claim that what will happen if we take the bracket between G alpha and G minus alpha. So, we claim that it must be at most one dimensional. So, let alpha in phi. So, then we have, so the bracket between G alpha and G minus alpha. So, that is subset of C T alpha. So, more precisely we can actually tell what will be the bracket in terms of the killing form. So, for example, if I take x in G alpha and then y is in G minus alpha. So, then if we take the bracket between these two elements bracket x y, so then that must be equal to kappa of x y times T alpha. So, recall that T alpha is defined to be defined using the killing form that is restricted to H. So, we identified H with H star using the killing form, in particularly given element pi inside H star. So, we associated this T pi inside H, so that the kappa of T pi comma x is nothing but pi of x for all x in H. Okay. So, using this equation the T pi's are defined uniquely. So, for alpha in phi we denoted T alpha by the corresponding elements. So, in particularly this T alpha is coming from that alpha. So, you have this bracket x y that is actually equal to kappa of x y times T alpha. So, in particularly the bracket G alpha comma G minus alpha. So, that is actually at most one dimensional. So, let us try to prove it. So, the proof is again simple computation. So, you take again alpha in phi and x in G alpha, y is in G minus alpha. Then for any h in H, let us compute for any h in H, let us compute this kappa of H comma bracket x y using the associativity of kappa. So, kappa of H comma the bracket x y. So, this is actually given by kappa of bracket H x comma y using the associativity. So, then this is exactly equal to, so recall the bracket H x is nothing but alpha of H x, okay, because x is coming from G alpha. So, in particularly this is nothing but alpha of H x. So, you get exactly equal to kappa of alpha of H x comma y. So, now you can take out this alpha of H. So, then you get alpha of H times this kappa of x comma y. So, now recall that. So, alpha of h is actually given by kappa of t alpha comma h. So, using this definition of t. Okay. So, we have this kappa of t pi comma x is nothing but pi of x for all x in h and pi in h star. So, in particularly we have this alpha of h equal to kappa of t alpha comma h. So, then if you substitute that there, then we get alpha of h to be kappa of t alpha comma h times this kappa of x comma y. So, now what we can do, we can take out this kappa of x comma y inside. So, then we get kappa of x comma y times t alpha comma h. So, this is equal to the kappa of h comma bracket x y. So, in particularly you can see that if we take, so this is a killing form being symmetric. So, this we can be rewritten as kappa of h comma kappa of x comma y t alpha. So, in particularly kappa of h. So, then you can take the difference between these two elements bracket x y minus kappa of x comma y t alpha. So, that must be 0 and this is true for any h in h. So, that means this element the bracket x y minus kappa of x comma y t alpha which is an element of h. So, this lies inside the radical of kappa when you restrict to h, but we know that kappa restricted to h is actually non-degenerate. So, in particularly this radical of k with respect to h is 0. So, that proves that this bracket x y minus kappa of x comma y t alpha must be 0. So, that is what we wanted to prove. We wanted to prove that the bracket x y is equal to kappa of x y times t alpha. So, this proves that if we take the bracket between g alpha and g minus alpha, so then this will be at most one dimensional. Indeed, we will prove in a minute this is actually going to be equal to that one dimensional space. So, that again like follows from this orthogonality between g alpha and g beta. So, let us prove that. So, here is the fourth statement. So, if we take alpha in phi, so then we have the bracket g alpha g minus alpha is equal to the one dimensional space spanned by t alpha. Okay, indeed what we do, you start with x non-zero element inside g alpha. So, then we claim that kappa of x comma g minus alpha must be non-zero. So, we claim that kappa of x comma g minus alpha must be non-zero. So, what will happen otherwise? So, otherwise the kappa of x comma g minus alpha will be 0, but then it is immediate that kappa of x comma g beta is 0 for all beta which is not equal to minus alpha. Okay. So, that means kappa of x comma g will become 0. So, that will imply that x will be in the radical of kappa with respect to g, but which is also 0. So, that is a contradiction because we started with x being non-zero. So, that means this proves that there exists. So, this proves that there exists y in g minus alpha such that kappa of x comma y must be non-zero. Then just to look at this x comma y, then if you compute the bracket x y, then we know that this is exactly equal to kappa of x comma y times t alpha. So, that proves that the bracket g alpha g minus alpha is being non-zero. So, that is actually being equal to the one dimensional space spanned by t alpha. So, this is something proves something about the bracket g alpha and g minus alpha. So, now if we actually think about a bit more, we can actually compute what will happen to alpha of t alpha. So, for alpha inside phi, so we claim that this alpha of t alpha, so which is by definition kappa of t alpha comma t alpha. So, this must be non-zero. Okay. So, all these things are later used to prove that there exists a nice SL2 subalgebra for each alpha and phi. Okay, that is where we are heading. So, let us first prove this. For alpha in phi, this alpha of T alpha must be non-zero. So, again this is done by contradiction. So, let us assume, okay, so assume that alpha of T alpha is 0. So, and then let us see what we get. If alpha of T alpha is 0, so then if we compute T alpha bracket x, then that must be equal to alpha of T alpha times x for x in G alpha. So, in particularly since alpha of T alpha is 0, so that implies T alpha x must be 0 and this is true for all x in G alpha. So, similarly we can prove that T alpha bracket with y also must be 0 for all y in G minus alpha, because again the bracket T alpha y will be minus alpha of T alpha times y, but alpha of T alpha is 0. So, that implies T alpha comma y is 0. So, now we can choose x and y as in 4, okay, as above. Choose x in G alpha and y in G minus alpha such that the bracket x y, which is kappa of x comma y T alpha, which is non-zero. Okay. So, then what we can do, we can replace y with some multiple of y. Okay. So, replace y with y times 1 divided by kappa of x comma y. So, then you can see that we can assume that kappa of x comma y being 1. So, by replacing this, we can assume that kappa of x comma y is actually equal to 1. So, now if we put together everything, so then what we get? So, we get the bracket x y is being T alpha and then the bracket T alpha x is being 0 and the bracket T alpha y is also being 0. So, that means if we take this capital S, which is the span of all this x, y and T alpha. So, this is going to define 3-dimensional solvable subalgebra of G. Okay. So, now if we look at it, so this add map is actually 1 to 1. So, add is 1 to 1 from G to GL of G. So, in particularly if you restrict this add map to capital S, so then again that must be injective. So, this must be injective. So, in particularly add of this S, okay, let us put G to denote we are talking about add with respect to G. So, add G S, so this must be isomorphic to S, because we are simply restricted to the image and add G is injective when we restrict to S. So, now since add S G is actually being a subalgebra of GLG which is solvable. So, then we will be able to get a basis of G, so that the elements of this add S, so they look like upper triangular matrices. Okay. In particularly, so if we take any element add small s with respect to G, so where S is coming from the derived algebra of this capital S, then this add S must be nilpotent. So, we use the same basis that we have actually fixed, so that all the elements of add capital S, they look like upper triangular. Now, if S is coming from the derived algebra, then you can see that the commutator of this upper triangular matrices will become strictly upper triangular matrix. So, that would imply that this add S being actually nilpotent. So, this proves that if you take any element in the commutator, that must be nilpotent. But if we go back to the table, you can see that the bracket xy is being T alpha. Okay. So, that means this T alpha, so this is actually inside your the derived algebra bracket SS. So, that means add of T alpha, okay, that is actually nilpotent, but since this T alpha is actually coming from your carton. So, that implies add T alpha, add G T alpha, that must be actually semi simple. So, this is semi simple. So, you have a element which is both nilpotent and semi simple inside GL of G. So, that forces that element must be 0. So, since add G of T alpha is 0, since add G is actually injective map, that forces T alpha must be 0. So, that is a contradiction, because T alpha chosen to be non-zero element in H, that corresponds to a root alpha, the root alpha. So, this actually indeed proves that alpha of H alpha, alpha of T alpha cannot be actually 0. Okay. So, the assumption that we have made, that actually not correct. So, that forces that alpha of T alpha must be non-zero. So, in particularly kappa of T alpha comma T alpha, that also must be non-zero. So, now let us use this to establish this SL2 triple. Okay. So, for that let us fix alpha in phi. So, then what we do, we also fix some non-zero element x alpha inside your G alpha. So, then what we do, so then we can choose y alpha inside G minus alpha, such that the bracket x alpha y alpha is non-zero. Okay. So, then using that y alpha, we will be able to produce SL2 triple. So, basically given this data alpha in phi and x alpha non-zero element in G alpha. So, then we can choose y alpha inside G minus alpha, such that this x alpha y alpha and then x alpha y alpha, which we denoted by H alpha. So, this will make SL2 triple. So, what is the meaning of this? The span of this will be isomorphic to SL2 of C, such that the span of this is naturally isomorphic to SL2 of C. So, and this isomorphism given very explicitly by sending x alpha to this upper triangular matrix 0 1 0 0, and then this y alpha to this lower triangular matrix 0 1 0 0, and this H alpha to this diagonal matrix 1 minus 1. Okay. So, this is the explicit isomorphism that is actually takes this x alpha y alpha H alpha to respective elements in SL2C. So, to prove this we have done already enough work. So, let us just rescale things and then get this SL2 triple. So, we fix this x alpha, which is coming from G alpha. So, let us say this is the given non-zero element. So, now since kappa of G alpha comma G minus alpha is actually non-zero, kappa of G alpha G minus alpha is non-zero. So, that implies that we can choose y alpha, which is again non-zero element inside G minus alpha, such that kappa of x alpha comma y alpha. So, that is exactly equal to twice divided by kappa of T alpha comma T alpha. Okay. So, because this kappa of G alpha comma G minus alpha, because this is non-zero. So, this has to be equal to complex numbers, entire complex numbers. So, we will be able to choose y alpha such that this happens. So, now what we do, so we just set this H alpha to be this scalar multiple of T alpha, the scalar being this 2 divided by kappa of T alpha T alpha. So, take H alpha to be twice T alpha divided by kappa of T alpha comma T alpha. So, then what happens if we do the computation, we can see that the bracket x alpha y alpha, which we already computed it to be, this is equal to exactly kappa of x alpha comma y alpha times t alpha. So, now since kappa of x alpha y alpha is given to be 2 divided by kappa of t alpha. So, then you can see that this is exactly equal to h alpha. So, now moreover if you compute h alpha comma x, then you can see that this is nothing but given by alpha of h alpha times x for x in g alpha. Okay. So, in particularly you can see that alpha of h alpha is given to be, so h alpha is nothing but what, twice t alpha divided by kappa of t alpha. So, then we get alpha of h alpha equal to twice alpha of t alpha divided by kappa of t alpha comma t alpha. But note that kappa of t alpha comma t alpha is nothing but alpha of t alpha. So, that means, so this part is actually get cancelled and then we get 2. So, alpha of h alpha is nothing but 2. So, this says that the bracket h alpha x alpha, so that must be twice x alpha. Similarly, if you compute the bracket x alpha y alpha, since y alpha is coming from g minus alpha, so you get minus 2 y alpha. So, now we can write down all the table. So, we have this bracket x h alpha x alpha is being 2 x alpha and bracket h alpha y alpha is being minus 2 y alpha, and note that the bracket x alpha y alpha, that is nothing but h alpha. So, this is exactly the product table for SL2C. So, that means the span of x alpha y alpha h alpha, that must be isomorphic to this SL2C. Okay. So, this tuple triple, okay, for alpha in phi. So, this 3-dimensional subalgebra which is spanned by this x alpha, y alpha and h alpha. So, that will be called the SL2 triple of corresponding to this alpha. Okay. So, this is the definition of SL2. So, naturally this is isomorphic to SL2. Okay. So, if we think about it, this association alpha to h alpha, so that is also somewhat a very nice association. So, let us make this remark. So, recall h alpha is given by twice t alpha divided by kappa of t alpha. So, but if we compute what happens to h of minus alpha, so then we can prove that this must be equal to minus of h alpha. So, this is again just comes from the definition. So, let us try to compute. So, what is the definition of h minus alpha? So, h minus alpha is given by twice t minus alpha divided by kappa of t minus alpha comma t minus alpha. But note that t minus alpha must be equal to minus t alpha, because this alpha goes to t alpha, that is a linear map in terms of alpha. So, that means this h minus alpha must be equal to minus 2 alpha divided by, so this is kappa of t pi comma t pi will be pi of t pi. So, this is just minus alpha of t minus alpha. So, then you get exactly equal to 2 t alpha divided by alpha of t alpha, sorry, minus, there is another minus. So, this says this is exactly equal to minus twice t alpha divided by kappa of t alpha comma t alpha. So, which is exactly minus h alpha. So, this proves that this h also behaves nicely with taking negative. So, h of minus alpha must be equal to minus h alpha. So, all these facts again will be used in order to prove more properties of this root system. So, let me just recall what we have done so far. So, we actually indeed proved that the span of phi must be h star and then 0 is not in phi, and if alpha is in phi, So, then that implies minus alpha is in phi. So, if we take this g alpha and g minus alpha. So, we proved that this must be a one dimensional space spanned by T alpha. So, by scaling T alpha we can also say that this is a one dimensional space spanned by this H alpha. So, now for alpha is in phi. So, we constructed for given any non-zero x alpha inside G alpha. So, we have constructed y alpha inside G minus alpha such that this x alpha, y alpha and then this H alpha which is defined to be the bracket x alpha, y alpha. So, this is actually forms SL2 alpha triple. So, this is the that means the span of this is isomorphic to SL2 of alpha. So, this is what we have proved so far. This is the very important result. So, on the way we also observe that alpha of T alpha. So, that must be non-zero which is kappa of T alpha comma T alpha. So, that must be non-zero. So, these are all things that we have proved. So, we will use these facts later and then actually we will prove actually more properties of the root systems. So, that I will actually do it in the next class. So, I will stop now. Thanks.